So now we transition to a discussion on stochastic processes. Here, again, it's a review topic, but it's an important review and something that's going to be at the core of the analysis of time series. The whole objective of the course is to understand time series, and in the context of modeling, a time series is in fact modeled as a realization of a stochastic process. So let's kind of recall what a stochastic process is. We think of it as a sequence of random variables, okay? In this particular case, the random variables are x to the minus t all the way to xt. So t runs from minus infinity to infinity over here, right? And so we think of, let me write it, t equals minus infinity to infinity. Symbol. Okay, and so what characterizes this particular set of random variables is that they do have a joint probability distribution. What does that mean? Is that mean for every finite number of these variables, there is a joint probability distribution that governs their occurrences, that governs the probability of any set of such finite variables, okay? So to be precise here, what we say is that there's the joint probability distribution of every finite sequence. Okay, so what does that mean? It means that if I observed, say, the process from x0 to x3, for example, over here, what do I have? I have three random variables, x0, x1, and x2. These will be governed by some joint probability distribution of x0, x1, and x2. So what does that mean? It means that the probability that x0, x1, and x2 lie in a certain part of the state space is governed by the probability distribution, the joint probability distribution that's given for this particular stochastic process. This is really hard to model, to say that I have every possible probability distribution of every possible finite sequence. So often we don't really deal with the underlying probability distribution. We do a simpler type analysis that we sort of will describe in a second. But for now, let's think of each one of those things as a random variable, and that there is a governing joint probability distribution of all of these different random variables. Because it's a random, each one of those is a random variable, we can define the mean of each individual element. So each one of those has a mean, and that mean is characterized by the quantity mu of t. Okay, so that's the expected value of x of t. What does that actually mean to us? Okay, because it's a random variable, it has a mean. Okay, and so we can just compute the expectation over, in this particular case, the marginal probability distribution of x of t. Because x of t is governed by a marginal probability distribution, you can compute the mean of that process. In reality and how we think about stochastic processes, we think, okay, you know, we're going to have observations of this complicated time series. Every time the universe starts, we roll out the dice and a sequence of such random variables occurs. A new universe, we roll out the dice for minus infinity, a new sequence is generated for the stochastic processes. So in a sense, what this probability distribution description is doing, it's telling us what a realization of potential observation of this stochastic process looks like. What are the most probable values that are correlated and connected dependently, are dependent on each other as we realize the stochastic process. So in that sense, there is a mean for every value of these random variables. Equivalently, there is also a autocovariance, and the definition of autocovariance of the stochastic process is just basically if you pick any two variables, okay, you can actually compute the covariance of these two variables. So how do you pick any two variables? They're indexed by any parameter t1 and t2. Okay, so if I take x of t1, that's one random variable, xt2, that's another random variable. Of course, all the random variables are indexed by time. So by picking any of two of these, I can compute the covariance of x of t1 and x of t2. How do I do this? It's just by definition, this is definition, the expected value of xt1 minus its mean times xt2 minus its mean. When you manipulate this expression, it looks like this is what we call the correlation function, R of T1 and T2 minus mu T1 times mu of T1 times mu of T2. So this is the product of the expectations, and this is the autocorrelation function that is defined precisely as the expected value of xt1 times xt2. So this is something that we encounter all the time. When we have two random variables, we know how to compute their covariance. And this is the same. We can compute the covariance for every two of these random variables, and we index that covariance by the parameter T1 and T2. Why do we do that? Because we're implicitly assuming that we're doing all of this for that one particular stochastic process. And the only thing that matters is what the value of T1 and what the value of T2, what the location of the x's are, which is indexed by T1 and T2. Okay. The variance, of course, is just the covariance of xt and xt, right? When T1 and T2 are the same. And so we write this RTT minus mu of T squared. So that's the equation for the variance. It's basically plugging in essentially the quantity of T1 equals T2 equals to T. That's the variance. And we can, in that way, generate exactly the expression for it as well. Okay, so these are a bunch of definitions, right, related to a stochastic process, which I review by saying it's just a sequence of random variables. A very important class of stochastic processes are ones that are called wide-sense stationary processes. We give them the notation as WSS, wide-sense stationary. And the wide-sense stationary process is characterized by its second-order statistics. It's really through the expectation and the autocovariance. Okay? So the first thing that characterizes a wide-sense stationary process is that the mean is actually independent of time. The mean is the same, mu of t is equal to mu, independently of any time. So every variable of this stochastic process is the same expectation. The second important characteristic of a wide-sense stationary process is what we call the autocovariance, or the correlation function, RT1 and T2, is only a function of the difference of T1 minus T2. That is a function of the lag, not a function of the actual location of T1 and T2. So if I'm interested in the covariance between 4 and 2, it's the same as 6 and 4. It's the same as 8 and 6. It doesn't really care about the location. It only cares about the difference between the two that we refer to as a lag. And often we give this expression a tau. And we say that RT1 and T2 is really just a function of tau, where tau is T2 minus T1. Okay, or T1 minus T2. And of course, as we know, the correlation function is symmetric, and so T1 minus T2 and T2 minus T1 is the same description, sorry. Okay, so this is T1 minus T2, but it doesn't matter. T2 minus T1 also provides the same autocorrelation function. So that's an important characterization, and we need some property like this stationarity in the future to be able to learn the underlying stochastic process, or a model of the stochastic process. This is going to come out in the future. It's going to be very important. Why? Because if we don't have stationarity, and the second order statistics characterized by expectation and covariance keep changing as time progresses, then by observing a certain finite sequence of the stochastic process, it's going to be hard to model the underlying process. So stationarity will emerge as a very important property for us to guarantee that we can actually learn the underlying process. That's not to say that we cannot learn non-stationary processes, but there's going to be a lot more structure for them in the future. Okay.